Question 11 is combustion analysis question. We're given a 1.375 gram sample of mannitol, which is sugar found in seaweed, and is containing carbon, hydrogen, and oxygen. It's burned in oxygen to give 1.993 grams of carbon dioxide and 0.9519 grams of water. What's the empirical formula? So the idea here is we're given a sample with a total mass equal to 1.375 grams, and that contains carbon, hydrogen, and oxygen, so we can say that that is equal to the mass of carbon plus the mass of hydrogen plus the mass of oxygen. So what we're doing is we're taking this compound, which is CHYOZ, and we're going to be burning this in oxygen to give CO2 and water. So we know all the carbon in the CO2 must come from the carbon in our compound, so that will get the coefficient X. And for water, every 2 hydrogens in the compound will give us 1 water, so the coefficient in front of the water will be Y/2. All right, so what we're going to be doing is using the mass of carbon dioxide and the mass of water to find the masses and moles of carbon and hydrogen in the compound, and then we find oxygen by subtraction, by difference. So we're going to start out with the CO2. We could say that the moles of CO2 that is produced is mass over molar mass is 1.993 grams over 44.01 grams per mole. That equals 0.0453 mole. Great. We do the same thing for our water. The moles of water that we form, mass over molar mass, 0.9519 grams over 18.02 grams per mole, 0.0528 mole. All right, great. So the moles of carbon that must have been in our original compound and the moles of hydrogen we can get from these values we have now. So we can say that the moles of carbon, which is, I guess, what we're starting with here, it's got to be equal to the moles of CO2 produced because they are in a 1-to-1 ratio. 0.0453 mole. Moles of hydrogen is going to be equal to our moles of water times 2, because there's 2 hydrogens in each water. CO2 and water to moles of carbon and hydrogen, and from here what we're going to be doing is going to mass of carbon and hydrogen, which goes back to our original formula right at the very top. We can get from moles of hydrogen to mass of hydrogen, and moles of carbon down here to mass of carbon up here. hydrogen plus mass oxygen, we now have mass total, mass carbon, and mass hydrogen, so we can use this equation to find mass of oxygen. To 5 grams. That's our mass of oxygen, which we can turn into moles of oxygen. Moles is mass over molar mass. Now we have moles of carbon, 453 mole. Moles of hydrogen is 0.1056 mole. Moles of oxygen is 0.05. Why am I doing that? 453 mole. So we can get the ratio of these three. We like it to be in whole numbers, so we can divide by the smallest to get it in whole numbers, which is 0.0453. That equals 1. That equals 2.33, and that equals 1. So that's not quite whole numbers yet. If you multiply them all out by 3, then you get 3, 8, and 3. So we can say our empirical formula then will be C3H8O3. And that's it. Question 12 says, tetraphosphorus hexaoxide P4O6 is formed by the reaction of phosphorus with oxygen as shown. The mixture of 75.3 grams of phosphorus and 38.7 grams of oxygen produce blah, 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 blah. What's the percent yield for the reaction? So what we need to do is calculate the theoretical yield and compare that with our actual yield, which is given in the question, and the ratio of the two will be the percent yield. All right, so we're going to first convert our masses of phosphorus and oxygen into moles, because we always use moles when we do stoichiometry. The moles of P4 is mass over molar mass, 75.3 grams over 123.88 grams per mole, which is equal to 0.6078 mole. Moles of O2, mass over molar mass, 38.7 grams over 32.00 grams per mole is 1.210 moles. All right, there's clearly more oxygen than there is phosphorus here in terms of moles, but we have to keep in mind we have this ratio of 1 to 3 in our balanced equation. So what we can do to find out what's limiting is divide each of these numbers by the coefficient in front of it in the equation. So that's what we'll do for the phosphorus. Divided by 1, 0.6078 And for the oxygen, there's a 3 in front of it, so it gets divided by 3 and becomes 0.403. This one is smaller. That means the oxygen will be limiting. Great. These numbers in red we'll never use again. We just divided them by the coefficients to figure out what's limiting, and then after that point, we're done. So you can just cross them out at this point, so you don't accidentally stick them back in somewhere. All right, so the theoretical yield in terms of moles of P4O6 will be equal to the moles of oxygen times the ratio of the coefficients. So there's a 1 in front of P4O6, and divide that by the 3 that's in front of the O2. That equals 1.210 mole times 1 over 3 equals 0.403. Turns out we did need that number again, but it was just a coincidence that it turned out to be the same. So that's our theoretical yield in terms of moles. Let's figure out what that should be in terms of mass. That's going to be equal to the number of moles times the molar mass, 0.403 mole. Molar mass is given up in the question, 219.88 grams per mole. And that works out to 88.66 grams. Our actual yield was a lot less than that. It was 43.3 grams. So we can get our percent yield divided by our 88.66 grams times 100%, which works out to be 48.8%, which we might call a moderate yield. It's not great, but not terrible either necessarily. Question 13. A chemistry student determined that the empirical formula for tungsten oxide. To do so, he heated 8.820 grams of tungsten with oxygen in a crucible and formed 11.878 grams of tungsten oxide. So this 11.878 grams of tungsten oxide is a combination of a mass of tungsten and a mass of oxygen. We know what the mass of tungsten is. Okay, so the mass of tungsten is given as 8.820. So the amount of oxygen is going to be equal to the total minus the mass of tungsten and this works out to 3.058 grams. So we have the mass of tungsten, mass of oxygen. We can convert now how much heat is absorbed or released when 40 grams of NH3 reacts in the presence of excess oxygen to produce NO and H2O according to the following chemical equation, which thankfully is already balanced for us. So delta H for this reaction is positive, which means you can consider the energy there as a reactant. Energy is being consumed. We could almost rewrite this equation if we wanted to look like this: 4 NH3 plus 5O2 plus 1168 kilojoules goes to 4 NO plus 6 water. Okay, so what we want to do is figure out for 40 grams of ammonia how much heat is going to be absorbed as part of that process. So we need to convert, first of all, our mass into moles because it's a stoichiometry question. So our moles of NH3 is mass over molar mass. 40.00 grams divided by the molar mass of ammonia, 17.03 grams per mole, is 2.349 moles. Okay, so the heat absorbed that we see is that you get 1168 kilojoules of heat absorbed for 4 moles of NH3 according to our balanced equation. So I guess the question is, how many kilojoules get absorbed for 2.349 moles? And the way we can answer this is by setting up a ratio where we have 1168 kilojoules over 4 equals X over 2.349. And then just solve for X. So X is equal to 1168 kilojoules over 4 moles times 2.349 moles, which is equal to 685.9 kilojoules. And that's absorbed. It says absorbed or released. It's absorbed because this is endothermic. Question 16. A 0.150 molar sodium chloride solution is referred to as a physiological saline solution because it has the same concentration of salts as human blood. Calculate the mass of solute needed to prepare 275 mils of a physiological saline solution. So we know what the concentration is that we want to make. Moles per liter. And we know the volume we want to make is 275.0 mils. So what we want to do is find out how many moles of sodium chloride we have to add to make that much saline solution. So the moles of NaCl will be equal to concentration times volume, which is equal to 0.150 molar times 0.275 liters is 0.04125 mole. We want to figure what that out is in mass, because it says the mass of solute needed to prepare. So mass is equal just to moles times molarity, or sorry, not molarity, molar mass is 0.04125 moles times the molar mass for sodium chloride, which is 58.44, and that equals 2.411 grams. Our original concentration only had 3 sig figs up top, so our answer should also have 3 sig figs, which is 2.41 grams. 17. What will the final volume of a solution prepared by diluting 25 mils of 8.25 molar sodium hydroxide to a final concentration of 2.40 molar? So we're going to use the equation here. This is a dilution question. C1V1 equals C2V2. And this is giving us what the initial volume is. And it gives us the initial concentration. And it tells us what the concentration final is going to be. And what we need to do is figure out the final volume. So V2 will be equal to C1 V1 over C2 equals concentration 1 is 8.25 molar. Initial volume is 25 milliliters. Divide that by the final concentration, 2.40 molar. And this is equal to 85.9 mils. And again for sig figs, this is going to limit our sig figs up here to 25 mils, so we want 86 mils. Next question. Green light has a wavelength of 5,200 angstroms. Calculate the energy of 1 photon of green light. So our wavelength is equal to 5,200 angstroms. That's equal to 5,200 times 10 to the minus 10 meters, which is 5.200 times 10 to the minus 7 meters. And we're going to stick this into our equation, which is energy is equal to Planck's constant times the speed of light over the wavelength, which is 6.626 times 10 to the minus 34 joule seconds times the speed of light, which is 2.998 times 10 to the 8 meters per second. And that all gets divided by the wavelength, which is in meters. It's got to match our units above. 5.200 times 10 to the minus 7 meters. So you can see these units here go. So if we didn't convert that first to meters, we'd be in rough shape. The seconds also will cancel with each other, and we're left with units of joules. And the value here that we will end up getting is 3.82 times 10 to the minus 19 joules. All right. This one is a question that asks which of the following statements is true. So we can kind of go through these one at a time. This says A, microwaves have a lower frequency than radio waves. It's actually the other way around. They have a higher frequency than radio waves do. Radio waves are lower in energy and therefore lower frequency. So that one's false. B, all orbitals in a given atom are roughly the same size. That is not true. That's false as well. We know that the orbital size increases as n increases. So orbitals in shell 3 will be much bigger than orbitals in shell 1, for example. The emission spectrum of a particular element is always the same and can be used to identify the element. That is actually true. So we kind of stop there, but we can evaluate the next two statements as well. D says, since electrons have mass, we must always consider them to have particle properties and never wave-like properties. That's definitely false. We have to consider them as waves when we look at their behavior in atoms. That's the whole idea behind them arranging themselves into orbitals and shells and all that stuff. So basically all of quantum mechanics requires us to view electrons in terms of their wave-like properties. For E, the statement that it is impossible to know simultaneously the momentum and the position of a particle is called the Pauli exclusion principle. False. That's the uncertainty principle. So the correct answer is C, the only one of those that's true. Question 20. What is the de Broglie wavelength in meters of a proton with the given mass moving at 1,000 meters per second? So we kind of just put this into the de Broglie equation, which is lambda equals Planck's constant times m times v, where v is the speed, which is given. And we can put the data in here now. We have Planck's constant, which is 6.626 times 10 to the minus 34 joule seconds. And what we're going to actually do is use, well, I'll get to that in a minute. I'll show you why. For mass, we're going to be using the mass given in the question, 1.6726 times 10 to the minus 24 grams. And the speed is given as 1,000 meters per second. So the way this is set up at the moment, it's a bit of a mess because none of our units seem to really work out. The seconds are maybe up here at the top and the bottom, but that's about it. The rest kind of doesn't match. So what we're going to do is convert our units on the top, because we know that 1 joule is equal to 1 kilogram meter squared per second squared. So if we rewrite this as 6.626 times 10 to the minus 34 kilograms meter squared per second, because the second squared and the second squared here and the second here will partially cancel. Then on the bottom we have this mass now of the proton that's in grams, but that's the wrong unit. We want it in kilograms to match the unit on the top. So this becomes 1.6726 times 10 to the minus 27 kilograms. So now those units will be able to cancel. 1,000 meters per second is fine. That still matches the units up top. And this will have our kilograms cancel. It'll have our meters partially cancel, and it'll have the per seconds cancel. So what we're left with is meters up top, and this will be equal to 3.96 times 10 to the minus 10 meters. So this one is more unit manipulation really than anything else.